Welcome to part 3 of the video tutorial series on chemical reactions. This segment will focus on thermodynamics, the heat of reactions. Let's get started. Alright, so when we think about the word thermodynamics, think heat. And we can remember that heat is symbolized with the symbol Q. And we're going to relate this heat as it connects to reaction energies. So, energy is the capacity to do work or transfer heat. So in the context of chemical reactions, we're really focusing on the heat transfer. Down the road, we will be looking at this as it's related to biochemistry in the field of bioenergetics, where we'll see where the transfer of energy of reactions in our cells. And for our class, mostly like how the food that we eat becomes a source of energy within our body. So to be able to talk about energy, we should go over units of energy. And it's interesting, science and nutrition have taken a different approach. So the science definition of a calorie is the amount of heat energy required to raise the temperature of 1 gram of water by 1 degree C. So this is an example where we have to pay attention to the case. All right, so in science, it's a lowercase c. Alrighty, so however for food, for nutrition uses an uppercase C. So if we put an uppercase C here for a calorie, then this is telling us uppercase, this would be in nutrition or food. All right, so nutrition uses the uppercase. Calories. So there is a connection between the science and nutrition definitions of calorie. So 1 nutrition calorie with an uppercase C is equal to 1,000 science calories. And then in science, we'll keep going there. And so now let's link this to what we understand about metric prefixes, right? So what's another way to write 1,000 calories, right? That would be 1 kcal. All right. Within science, there is another unit system that we can also use. And so in the science world, 1 calorie is equal to 4.184 joules. All right, and so that uppercase J is symbolizing the energy unit of joule. So those are the 3 energy units that we will be using in this course. So before we get to reactions, let's make sure we understand these energy units. So let's say, for example, that we want to eat a muffin, and the label tells us that there are 350 calories, right? So we notice these are the nutrition calories or the food calories. Let's do a simple calculation to get this into joule energy. All right, so we start with what we know. We know we have a muffin with 350 nutrition calories. Now, we don't have a direct link between nutrition calories and joules. So we're going to go to the science calories. All right? So for every nutrition calorie with the uppercase C, we will have 1,000 science calories with the lowercase c. So when when you're doing quizzes and tests, you have to make sure that you're very careful with your penmanship so that you communicate your knowledge to your professor. All right, so now we have converted out of nutrition calories and into food calories. And so we can bring in now our calorie to joule conversion, that for every science calorie, that would correspond to 4.184 joule units. All right, So now we would punch this into our calculator, and the calculator is going to spit out a very large number. Now we know why the food industry doesn't use joules, right? Nobody would want to eat anything. The calories are overwhelming. And this is a good opportunity to do a review of sig figs, right? So what should we report here, right? We have 2 sig figs in our label of our muffin. This is a defined conversion, infinite sig figs, right? It's exact. And then we have a unit conversion between calories and joules, 4 sig figs. So in reporting this final answer, we would only want to report 2 sig figs. So remember that the sig figs are telling us that we know the 1 for certain, and then we're guessing here, right? This is our uncertainty. So we look to the right and we would round up. So in reporting our final answer on this muffin, we would say that the muffin has 1.5 million joules of energy. Wow. Okay, and if we wanted to write this in scientific notation, we would write it as 1.5 times 10 to the 6th. And either answer is fine. Okay, so now that we're comfortable with the units of heat and energy, let's connect those to reactions. So, when we talk about heat energy in relationship to reactions, we introduce a new term, enthalpy. Enthalpy is symbolized with the letter H. And because reactions are about change, right, our delta would be the change, right, in heat. And when we're talking about heat with respect to reactions, we use the term enthalpy. So linguistically, there's a little bit of vocabulary there. Okay? So the first law of thermodynamics, conservation of energy, specifically heat, says that but it refers to all forms of energy. Energy can neither be created nor destroyed. And so this is where we're going to connect the energy, right, that is held in the chemical bonds. We're going to relate that to the heat absorbed or released in a chemical reaction. Okay, so that's really the heart of this tutorial. So the delta H is the heat of the reaction. It describes the heat given off or absorbed, and we describe that as the reaction enthalpy. Okay, so we've already noticed, well, wait, the heat can be given off or absorbed. So we've got a few more terms to learn here. Exothermic and endothermic reactions. These are the terms we use to tell everybody which way the heat flows, right? Not all reactions release heat. Some reactions need heat to occur. So we have 2 different terms to describe these reactions. With an exothermic reaction, right, exo, exits, right? The reaction gives off heat. Heat exits the reaction. Right? So that, what is that telling us energetically about the products and the reactants? That's telling us that the products are lower in potential energy than the reactants. So we've talked about it linguistically. Let's look at it in terms of a graph. All right? So this will be the energy on the y-axis, increasing as we go up the scale. And then along the x-axis, we can just consider this the reaction progress. Sometimes you'll see it written as time, communicating the same idea. So for an exothermic reaction, right, the products are going to be lower than the reactants. So the reactants are higher in energy. and then the products are lower in energy. So we're just going over the fundamentals here, so we haven't been given a specific reaction. So we'll just write reactants and products here to hold the place. And now let's bring in this enthalpy term, right? So this is representing delta H, and because the final is lower, we would say this is a negative delta H, right? The energy is going to a lower state. So this represents the heat given off in the reaction. So this difference in energy between the reactants and products is the heat released during the reaction. Okay, and then to write this out one other way, so we've talked about it in terms of linguistics and with a graph. If we want to think in terms of a reaction, right, we would have our reactants, and they're going to produce a product, right, plus heat. Okay, so for an exothermic reaction, think of heat as a product. We'll compare this now to the endothermic reaction. So basically we're just going to take everything we just did and we're going to reverse it. We're going to use the same graph, same style, energy on our y-axis and reaction progress on our x-axis. But in this case now, right, the reaction absorbs heat. Why does it absorb heat? Because the products are higher in energy. So we have a low energy reactant producing a higher energy product. So when we draw the reaction enthalpy, the heat of the reaction here, we're going up, right? So that's the positive delta H. All right. So this represents the heat that must be added to the reaction for it to occur. So now we'll wrap up with showing this as a reaction now. So this would be saying that we have the reactants, and now we have to add heat to be able to produce the products. So in this case, right, we think of heat as a reactant. And whenever we're discussing a reaction, when we describe it in one direction, what is negative or positive enthalpy. If we reverse the reaction, we'll always change the sign. Alrighty. Now let's look at some real reactions so that we can put in actual chemical formulas and put this all together. So we'll go to the next page. Alright, so let's practice drawing the complete reaction energy diagram for each of the reactions below, making sure that we label our axes, the delta H, and include the chemical formulas of the reactants and products. Let's also classify the reactions as exothermic or endothermic. Now, the convention here, right, is that if we look at this reaction, methane with oxygen to produce CO2 and water, this negative sign here is telling us exothermic, right? Because we talked about exothermic being negative delta H. So this negative sign is telling us, right, that the heat is a product. Okay, so we can start drawing our reaction energy diagram. Energy is always along the y-axis, and reaction progress along the x. Make sure to get all the points. You're doing the work. All right. So heat's a product. That's telling us that the products, right, are lower in energy and the reactants are higher in energy. So we're going to draw our curve like this. If you're wondering about this lump, we will address this in our final video tutorial. So for right now, we'll focus on this part, right? So the enthalpy, it's the energy difference between the reactants and products. So there's our minus delta H. And in this case, we know it's minus 213 kcals per mole. So we've already labeled this one as exothermic. That will be more explicit. Okay, so now to finish this up, we're going to write, here we're not talking in general terms, we have a specific reaction. So the reactants are methane and oxygen, and the products are CO2, water, and then the heat described by the graph. All right, one more reaction practice. Slide this up. Okay, this is the other way to communicate the reaction enthalpy. Here we notice that the reaction enthalpy is included as a reactant. So because the enthalpy is shown as a reactant, we know that this reaction is endothermic. If this information was shared like the previous example, we would show it as delta H plus 43 kcals per mole. All right? So the positive sign would tell us it's endothermic, or how it's written as a reactant tells us endothermic. So for this reaction to occur, we must add energy or nothing will happen. All right, so our reaction energy diagram. Energy is always on the y-axis. Reaction progress on the x. So this time, right, we have to put energy in. So it means our reactants are lower in energy than our products. So we have to put in heat or energy, right? And this would be, in this case, we know how much or the minimum amount we have to put because we're given the value. And then to finish up our diagram, we will list the actual reactants and products for this reaction. Alrighty, so that will cover the main part of connecting reaction energies to the reaction, but there's a very important application of this concept, calorimetry, that comes full circle with nutrition and the calorie units we talked about on the first page. So let's now look at this important application of reaction energy. So calorimetry is an experimental technique to measure enthalpy changes, right? So enthalpy, delta H. So we're trying to measure that. So this relates to conservation of energy. The idea that the heat lost must equal the heat gained. All right, so to figure out, how did they figure out that there were 350 calories in that muffin? Right, well, what we're going to do is we're going to do a combustion reaction and we're going to burn the food, right? So the heat lost by the food is going to equal the heat gained by the calorimeter. So that's the device that's been designed to absorb all of this heat so that we know how much was released. Now, let's look at the construction of the calorimeter, right? So here's our food, and then we're going to have some ignition wires, right, to start combustion. And then for a combustion reaction to occur, right, we need some oxygen to be there, present. And then we have, this is all part of the calorimeter, and this has been designed in such a way to absorb the released heat. So the calorimeter absorbs the heat released from the food. Alrighty. And so then all of the measurements hinge on this thermometer. So there's a lot that goes into this, that details that we're not going to talk about. So basically there's a formula that's been derived that we can look at the change in the temperature, and we can connect the increase in the temperature can be correlated to the calorie content of the food. All right, so when we're not going to worry about those details, we just want to understand the overall concept, right? So a formula converts, right, the change in temperature, the increase in temperature, to, right, the calorie content of the food. And since we're talking about food, we're using uppercase C. And so this, of course, is a subject that has been studied to a great detail. And so what have we learned about food? Well, as we go through the course, we're going to recognize that food is comprised of basically 3 biomolecules: carbohydrates, proteins, and fats. And here's some examples of where we would find those. And then we'll notice that the calorie content per gram of carbohydrates or proteins is the same. Fats are a very high energy molecule, so we get more calories from each gram of fat that we consume. So in my class, I don't expect you to memorize this. I'll include this information on any questions. Let's finish up by practicing a calculation. All right? So I think this was some granola. I photocopied a label off of some granola. And let's calculate the calorie content for each of the biological molecules on the nutritional label. Well, since the label starts with fat, let's start there. There are 9 grams of fat in a serving of this granola. So for fats, all right, we start with the number of grams of fat we would have. And then we would look to our table, and our table tells us that there are 9 calories of heat energy for every 1 gram of fat. And then we have to have careful attention when we're reading these questions, because notice that that's a science calorie. So we have been given the information in food calories. So we're going to need to weave in, right, for every food calorie, we would have 1,000 science calories. So we punch these values into our calculator, and it's going to spit out 81,000 science calories. And then we'll take this opportunity to do a sig fig review. This can be very unsatisfying though, because everything has one sig fig. So if we were going to report this, we would say that we have 80,000 calories from the fat. And now we'll repeat this process 2 more times. Let's look at the let's see what's next on our label. We have carbohydrates here. So we'll go ahead and do the carbs. So we would have 16 grams of carbohydrates. And then our chart tells us that for every gram of carbohydrates, we will receive 4 calories of energy. And then we will convert that from food to science calories. And our calculator spits out a value of 64,000 science calories. And once again, we're limited to 1 sig fig. So if we're watching our weight, that's a good thing. Only 60,000 calories from those carbs. And then last but not least, we'll look at the protein. So the protein on our label is 3 grams. 3 grams protein. Our chart tells us there are 4 calories for each gram of protein. And then, last but not least, the question wants to know in science calories. So we'll do that last conversion step. And our calculator spits out 12,000 science calories. But we're limited to 1 sig fig, so we would report the answer as 10,000 calories. Okay, so this tutorial was very all-encompassing. It introduced the energy units of calories, both scientific and nutrition, and joules, looked at how it connects to chemical reactivity with endothermic and exothermic reactions, and finally a very useful application with calorimetry. Please take some time now to work a few practice problems to reinforce your understanding.